Okay, in this lecture, we're going to learn how to take a chemical formula and write a chemical name associated with it, as well as do the opposite, that is to take a chemical name and write a chemical formula. Now, what we went over last time on Thursday was how to name ionic compounds, right? So the first step that you need to know when you look at your formula is to identify the elements that are in there. Are they metals? Are they nonmetals? If you have a metal and a nonmetal combination, you name it like an ionic compound. If all of the elements are nonmetals, you name it like a molecular compound shown here. And if the compound has a property of an acid, you name it differently. All right, so let's review very briefly what we covered last time on ionic compounds. The main distinction is being able to identify which metal type you have in your compound, whether it's type 1 or type 2, right? So we told you to memorize all of these metal ions and their charges. These elements, when they form an ionic compound, always have this charge. It's guaranteed. So all the alkali metals are +1. All the alkaline earths are +2 when they form ionic compounds, and the other three metals for which the charge is invariant is aluminum +3, zinc +2, silver +1. So just memorize those. Now, on the other side, the other component of an ionic compound are non-metal elements, right? So the combinations were actually the charges, rather, that the following nonmetals form also never vary. The halogens in the 7A group are always -1, so we have fluoride, chloride, bromide, iodide. The chalcogens in 6A are always -2, that's oxide, sulfide, selenide, and telluride. And the pnictogens in 5A, the first three members, are nitride, phosphide, and arsenide. All right, so you need to be able to memorize those. Now, if we take a name, we went over this stuff last time, but if you take a name like barium bromide, right? Notice that in the name, there's no indication about the relative numbers of species, but you have all the information that you need. Why? Because bromide is always -1, and barium is always +2 when they form ionic compounds. So you know that to write a chemical formula which is electrically neutral, that is when you sum up all the charges of the ions, you better get 0, then you know that you need 2 bromide ions at -1 charge each to balance the charge of barium +2. So you would write the formula BaBr2. All right, so how can you identify a type 2 metal ion? Well, because it's not type 1, right? If we go back and look here at our type 1 metal ions, all the spaces that are here that are empty are places where other metal elements would be, and their charges can vary. So how do you figure out what charge you have? Well, it depends on what it's bonded to. So for example, there's two different compounds of copper chloride and two different compounds of iron oxide. So there's not enough information if you just say the name copper chloride, because it's not clear which compound you're talking about. So that's why we incorporate the charge of the metal ion as a Roman numeral when we name it. So for example, if you look at the formula here, CuCl, you know chloride is always -1 when it forms an ionic compound. That forces the metal to be +1. That's how you figure it out. So you'd name this compound copper 1 chloride. And in this case, since we have two chlorides at -1 each, the copper here must be +2. So we name that copper 2 chloride. So I hope you see that this naming process for the ionic compounds, at least so far, is purely rational. It just makes sense. If we look at the name for iron 2 oxide, right, there's no ambiguity on what the structure is. Oxide is always -2. Iron, in this case, you're being told is +2, so you just write the formula as a 1-to-1 ratio, iron, oxide. In the case of iron 3 oxide, again, you know that oxide's -2, and you're told that iron has a +3 charge. So this is a little more complicated. So what you need to do here is think about, well, what's the least common multiple, right, where we can get these charges to balance. And the least common multiple is 6. You take -2, multiply it by 3, you get -6. You take +3, you multiply it by 2, you get plus 6, right? So plus 6 minus 6 equals 0. So you would write your formula as a 2 to 3 ratio of iron to oxygen. All right, so that basically leaves us where we left off in lecture on Thursday. It turns out that there's some ionic compounds that have incorporated in the crystalline lattice discrete water molecules that you can count relative to the number of ionic formula units. So for example, if we look at the formula down here, we can see that we've got an ionic compound, right? Iron and chlorine. Chlorine is always -1, and we have 3 of them in the formula. Iron, well, it's a type 2 metal ion, and you can tell that you must have a +3 charge here to balance the 3 chlorides. So we begin writing this compound out as iron 3 chloride. Now, the rest of the formula here, the .6H2O, means that for every one of these iron 3 chloride units, you have 6 water molecules nearby in the crystalline lattice. And so to write out the formula, we use a Greek prefix to count out the number of water molecules. So now we would name this compound iron 3 chloride hexahydrate. The Greek prefix for 6 is hexa. Let's look at the other 3 compounds we have up here. We're introducing something new, and that is a molecular species that's embedded within the ionic compound. The molecular species here is sulfate. That's shown out here. It consists of 5 nonmetal atoms to form a molecule, sulfur and 4 oxygens. However, the molecule has a charge. It's -2. We call these polyatomic ions. You're going to see a bunch more in a moment. All right, so if we have sulfate, the -2 charge has to be counterbalanced by the metal cation. And in the case of the first example, the metal cation is copper +2. So it's a 1-to-1 ratio of copper to the polyatomic ion. So we would name this copper 2 sulfate. Now for every copper 2 sulfate formula unit, we also have 5 water molecules in the crystalline lattice. So we name this copper 2 sulfate pentahydrate, penta meaning 5. The one below it has calcium, which is a type 1 metal ion. It's +2. So all we need to do here is just name this calcium sulfate dihydrate. Just a little point of interest. This calcium sulfate dihydrate is also known as a mineral gypsum, and gypsum was one of the very first binding mortars that was invented by the Egyptians to bind the stones of the pyramids that they built in the latter part of their civilization. So how they did this is they would just take gypsum, they put it in a kiln, a very hot oven, and heated it up to at least 800 degrees Celsius. At that temperature, you drive off most of the water, and what's remaining behind is this plaster of Paris. It's calcium sulfate hemihydrate, hemi meaning half. And so they were able to take this plaster of Paris, mix it with just the right quantity of water, some gravel, sometimes sand, a little bit of lime, which is calcium carbonate, to make gypsum mortar. All right, so go ahead and turn off the video for a moment and try to name these on your own without any access to notes. All right, so for the first one, right, we have barium, which is a type 1 metal ion. It's always +2, so no need to use Roman numerals. We just name it barium chloride dihydrate. For the second one, however, nickel's type 2 metal ion. So we have to figure out its charge. Well, we have 2 fluorides. Each one we know is -1 because you've memorized it. And therefore, that requires nickel to be +2. So we would name this compound nickel 2 fluoride tetrahydrate, tetra meaning 4. All right, so far we've named the ionic compounds. Now let's look at the molecular ones. You see the distinction in the logic in naming these 2 different classes of compounds is that with ions, you have information about the relative numbers of species in your chemical formula because of the charges involved. However, with nonmetals, right, molecular compounds consisting of nonmetals, for right now, I just want you to assume that all of the charges of all the elements in a molecular compound are 0. We'll talk about this in more detail later when we get to bonding. It's not exactly true, but for simplicity right now, assume that they're 0. So there's really no way that you would be able to count from just a name, right, the numbers of things in a formula if you didn't provide some information. So we use prefixes, the Greek prefixes, to count the relative numbers of these species. So here are 4 examples. We look at P2S5, for example. We have 2 phosphorus atoms and 5 sulfur atoms in the structure. So we would name this diphosphorus pentasulfide. Here are the Greek prefixes that you need to know. So there's di for 2, penta is 5. You need to memorize all these and use them appropriately. Now, a couple of caveats when you're doing the naming. The first element, if it has more than one of that first element, then you need to use a prefix. But if there's only one, there's no need to use mono. We only use mono to count second, third, fourth, fifth elements, etc. So, for example, we would name this carbon monoxide. No need to call it monocarbon monoxide. The second one, we call it carbon dioxide. And another thing, for N2O4, you would think you would just name it dinitrogen tetraoxide, but in that case you get double vowels, A and O, linked together. And generally what we do is we drop the first vowel. All right, so in addition, the order of the elements. Generically, we put the element that's furthest to the left in the periodic table first. So we put N in front of the fluorine and NF3, and we would call this compound nitrogen trifluoride. This we've already mentioned. You omit mono from the first element if there's only one, and we remove the first vowel if we have double vowels. So we would say diphosphorus pentoxide, not diphosphorus pentaoxide. Now, in addition, there are a number of molecules that have been around for a long time, well before the systematic naming process. So typically for these, we just use the common usage name. So for example, NH3, using the naming scheme, we would say nitrogen trihydride. But nobody ever calls ammonia nitrogen trihydride. We just call it ammonia. And the same thing for water. It's H2O. You would call it dihydrogen monoxide, but nobody ever calls it that. Just call it water. All right, so go ahead and turn off the video and attempt to name these 3, and then I'll give you the answers. All right, so for the first one, right, verify first of all that all of these are molecular, right? So bromine and fluorine are both nonmetals. So are phosphorus and sulfur, chlorine and oxygen. So we would name them in the following way: bromine pentafluoride, tetraphosphorus hexasulfide, and the last one is dichlorine heptoxide. All right, now at this point we would go ahead and deal with the acids, but instead we're going to go back and look at a special case of ionic compounds, those that contain polyatomic ions. We've already seen some examples of this, the copper sulfate and the calcium sulfate. So on this slide we're going to show you a whole bunch of these molecular species that you need to memorize. The positively charged ones are called cations, and you only need to know 2. The first one's ammonium. It consists of 5 atoms, 1 nitrogen, 4 hydrogens that are bonded together to form a molecule. The overall charge of the molecule is +1, so we write it as NH4 with a superscript plus. This other one's interesting. It consists of 2 mercury atoms bonded together to form a molecule, and the overall charge of the molecule is 2+. Since you have 2 atoms, then that requires each atom to have a +1 charge. So that's called the mercury 1 dication or the mercurous ion. You don't need to memorize this language here, mercurous. However, you do need to memorize all of these negatively charged species are called anions. You need to know the names, you need to know the formulas, and you need to remember the charge for each of these species in the formula. To help you minimize the amount of memorization you need to do, I recommend that all of the polyatomic ions that have an ATE ending, that you absolutely memorize those first, and I'll show you a simple mnemonic device to help you remember how to get the others. So for example, nitrite. To get this one, it's one oxygen atom less than nitrate. So if you remember nitrate is NO3 minus, you can get nitrite by just remembering the one with the ITE ending is one oxygen atom less than the molecular ion with the ATE ending. So this would be NO2 minus. Same thing with sulfate. Sulfate, memorize it's SO4 2 minus. Then to get sulfite, you just remember, okay, the one with ITE ending is one oxygen atom less. So you take sulfate, SO4 2 minus, remove an oxygen. You get SO3 2 minus. That should cut down on your on the number that you need to memorize, because there's a whole bunch of them, folks. Here's dichromate, permanganate, phosphate, carbonate. Acetate has two representations for showing this. We'll talk a little bit about this particular one later when we describe naming organic compounds. And we also have cyanide and thiocyanate. But there's a bunch more, folks. You need to read section 2.8 of your text, and as you're reading it, every single polyatomic ion that you encounter in that section, you should write down and make a list, the name, the formula, the charge, and memorize them. All right, so we've already talked about how to name the, or basically to get the formulas for the names with the IT ending, right? Remember the ones with the AT ending and then remove an oxygen to get the ones with the ITE ending. All right, so there's two prefixes that we also use to count the number of oxygens in our compound, in our molecular ion rather. For chlorate, that's the one that you would remember, right? A ClO3 minus, you get chlorite by removing an oxygen, so that would be ClO2 minus. Hyper and hypo are Greek prefixes. Hypo means under, right? Think of hypodermic needle or hypothermia, right? It means under. So when we use the Greek prefix hypo, it's one less or one under chlorite in this case. So we would remove one more oxygen. From chlorite, you end up with hypochlorite, ClO minus. By the way, this polyatomic ion, ClO minus, is the principal component in Clorox or bleach. It comes in two forms. If you look at the ingredients on your bottle of bleach, you'll see sodium hypochlorite, that's NaClO, as well as hypochlorous acid. We haven't talked about naming acids yet, but that compound is HClO. All right, so perchlorate, right? Per or hyper means above, so this is adding an oxygen to the one with the chlorate ending. So perchlorate is one oxygen atom more, so that would be ClO4 minus. All right, the last thing that we need to talk about here are additions of hydrogen ions to polyatomic molecules to make new ones. So for example, if we take a hydrogen ion, which is simply a hydrogen atom with its electron removed, it's just a proton, it has a +1 charge, right, shown here, H+. If we take H+ and add it to PO4 3- so that they're bound together, we generate a new polyatomic molecular anion. This case, HPO4, and now the charge is reduced by -1 because we've just added a positive charge to it. We would call this hydrogen phosphate, right, for this new polyatomic molecule. Now if we add two hydrogen ions or two protons to phosphate, the charge drops by 2 units. So this is H2PO4-, and this is named dihydrogen phosphate. So what would you get if you added 3 hydrogen ions to phosphate, right? Well, you would get an electrically neutral compound, H3PO4, and you would think, logically, you would just call it trihydrogen phosphate. But unfortunately, it's an acid and is named separately. We'll talk about that later. All right, so for all of these polyatomic ions that have a charge greater than -1, it's possible to protonate them or add hydrogen ions to them. So sulfate, we can add a hydrogen ion to form hydrogen sulfate. Adding 2 protons to form H2SO4 is not dihydrogen sulfate. It's an acid, H2SO4, and we name it differently. All right, so let's review our naming for ionic compounds that contain polyatomic ions. Look at the name here for potassium carbonate. All of the information that we need to write the formula is inherent in our name. Carbonate, you just have to remember, right, by rote memorization that carbonate is CO3 2-. Potassium is a type 1 metal ion, it's always +1. So to counterbalance the -2 charge of carbonate, you need 2 potassium ions, so you'd write the formula K2CO3. Cobalt-3 nitrate, same thing. We have all the information that we need here. Nitrate, you just have to remember, has the formula NO3 with a -1 charge. Cobalt, given here, is a +3 ion, and so we recognize we need 3 nitrate molecular ions to counterbalance the +3 charge for cobalt. So we write the formula in the following way. We have our cobalt. We write a bracket around our polyatomic ion, NO3-, and then we put a subscript counting 3 individual nitrate polyatomic ions in our formula. So our formula really consists of 4 pieces, a cobalt +3 ion and 3 nitrate ions. Then we name all the others in the same way. You just have to memorize your polyatomic ions. In the last example, sodium hydrogen phosphate, right? The hydrogen phosphate is a polyatomic ion that has the formula HPO4 -2. And as a consequence, we need 2 sodium +1 ions to counterbalance that charge. So this is sodium hydrogen phosphate. We don't have to say disodium hydrogen phosphate. Everything that we need to write the formula is inherent in the name. If we had the formula NaH2PO4, so we had the molecular ion dihydrogen phosphate, we would name that sodium dihydrogen phosphate. All right, go ahead and pause the video and attempt to name the following 3, and then I'll give you the answer. All right, so for the first one, you just have to recognize that this is your polyatomic ion. It's MnO4-, and it has the name permanganate. So we would name this potassium permanganate. And the second example, well, you may not remember this polyatomic ion, but I told you that you should absolutely remember the ones with the AT ending, right? ClO3- is named chlorate. 1 oxygen atom more, we use the per prefix. So this molecular ion is perchlorate with the same charge, -1. There are 3 perchlorates in our formula, which has to be counterbalanced with the charge of the metals. This is a type 2 metal ion, and so we can deduce that the charge here has to be +3. So we name this chromium-3 perchlorate. All right, in the last example, if you look at your list that you've accumulated from reading section 2.8 of your text, I don't think you're going to see this molecular ion, but you're responsible for it anyway, and here's why. If you look at it at a periodic table, you'll recognize that bromine is a halogen, right? It's in the same family as fluorine and chlorine and iodine. Now, we mentioned to you in class already that elements that are in the same family or same group have similar chemical properties. Basically, they have a tendency to react with the same element and the same relative numbers. So chlorine forms a compound with oxygen that's 1 to 3. we'd expect bromine to do the same thing and iodine to do the same thing. So ClO3 minus is chlorate, so BrO3 minus is bromate. Calcium's a +2 ion, so there's no need to specify its charge with a Roman numeral. We would just say calcium bromate. All right, well, we're finished naming inorganic compounds as well as the molecular compounds. I've already mentioned that the approach to naming those is definitely rational. It's logical. It all makes sense. But you're going to find for the acids that there's a breakdown in logic here, and this definitely causes some confusion the first time you look at it. So first of all, we need to define what is an acid. Can you recognize an acid when you see a molecule? Sorry, when you see a molecular formula. Well, there are many definitions for an acid, and the only one that we need to know right now, we'll see more when we cover chapter 4, but the only one we need to know right now is the Arrhenius definition, which specifies that an acid describes any compound that when it's dissolved in water breaks up in fragments to form protons or hydrogen ions, right, in water. So here are 4 examples. HCl is a molecular compound. It's a molecular compound that has hydrogen in it, and it just so happens that when you dissolve HCl in water, it doesn't remain as a diatomic molecule. It fragments into H+ ions and Cl- ions, or hydrogen ions and chloride ions. Hi has the same property. It dissolves in water, and when that happens, it fragments into ions. Same thing with H2S and HCN. So how do we name them? Well, we name them with hydro. We place the partial element name. So in the case of this compound, we would start hydrochlorine, right? But we drop the ene part. So it's hydrochlor, then add ic and acid, hydrochloric acid. For HI, we start off with hydroiodine, right? We drop the ene part, add ic and acid. So this is hydroiodic acid. In the case of H2S, we'd start off with hydrosulfur. Just add ic and acid, and you're done. Hydrosulfuric acid. HCN, we recognize that Cn minus is a polyatomic ion. It's one of the ones that you need to memorize. So we name this hydrocyanic acid. It's binary in the sense that when it dissolves in water, it fragments into 2 components. Although clearly cyanide consists of 2 atoms, right? It's a polyatomic molecule. We're going to see in a moment that there are a lot of acids that contain polyatomic ions that have oxygen as the main component of the polyatomic ion. They're named differently. This one, we just name it like a binary compound. All right, so far so good, but here's the first fly in the ointment. All right, so if you look carefully here, we've got in brackets with AQ. So what does that mean? It means aqueous solution, and it specifies that our compound is dissolved in water, so it's not pure. It's a mixture. It's a mixture of HCl, in this case, and H2O, water. And when it's in this form, you name it this way. But when HCl is pure, right, it happens to be a gas in its pure form, so we write G for gas phase, we name it like an ionic compound. And you're going, what? It's molecular. Why should I name it like an ionic compound? It doesn't make any sense at all. Well, if there is some rational basis to this naming mechanism, it's on the basis of how HCl behaves when you dissolve it in water. You see, even though it's molecular, when you dissolve HCl in water, it fragments into ions, so it behaves like an ionic compound, right? If you dissolve sodium chloride in water, it's an ionic compound, it fragments into ions. And since HCl behaves the same way, well, we name it like an ionic compound, so you name it hydrogen chloride. H2S is the same thing, right? So as an aqueous solution, you name it hydrosulfuric acid, but when it's in its pure form, it's a gas, H2S, we name it hydrogen sulfide. By the way, H2S is really nasty. If you've ever smelled a rotten egg, what you're smelling is hydrogen sulfide gas coming off of it. H2S is highly, highly toxic, and that's really why our noses have evolutionarily adapted so well for detecting it in such minute concentrations. You don't need very much at all. The natural gas that's piped into our homes for uses in stoves as well as heating water is spiked with a tiny, tiny, tiny little bit of hydrogen sulfide so that we can smell the gas. Methane is colorless and odorless, but you can definitely smell this. All right, so for naming acids, there's two branches in the tree. One is to name binary acids, that we've covered. The so-called oxoacids contain, if you look at the formula, they contain a polyatomic ion, which you can see by inspection if you've memorized your polyatomic ions. If we look at these four formulas here, you can recognize sulfate, nitrate, and carbonate. And in this particular case, you remember that ClO3 minus is chlorate. One oxygen atom less would make this polyatomic ion in the formula here chlorite. So the way you name them is the following. All of the oxoacids that have the polyatomic ion in them that ends with the ATE ending, you name it by using the partial element name, add ic and acid. So H2SO4, right? You don't name it dihydrogen sulfate, right? Instead, you call it sulfur and then add ic and acid, sulfuric acid. Remember H2S? That one is named, think about how it's named again, right? Hydrosulfuric acid. This is sulfuric acid, H2SO4. Nitrate and carbonate. So these are named nitric acid, carbonic acid. HClO2, because the polyatomic ion has IT ending, right? We name this with the OUS ending. So this is chlorous acid. If this formula were HClO3, we would call it chloric acid. All right, folks, that takes care of the naming business for the inorganic compounds. Now, we're going to look at some simple organic compounds. If you go on to take organic chemistry, you're going to see in much greater detail a fairly sophisticated naming system for all of the different types of organic compounds. So, organic compounds are essentially those that contain carbon. Hydrocarbons contain only hydrogen and carbon, and alkanes are a specific subset of hydrocarbons that contain only single bonds. Now, we'll specify when we get to bonding theory what we really mean by single bonds, but for right now, we'll just denote them as lines that connect the carbon atoms to the hydrogen atoms in the structure. One thing to memorize at this point is that carbon always forms 4 bonds. And so if we're going to form single bonds, carbon is going to form a bond with each hydrogen atom. Right? So that's represented in this structural formula. Now, if we cleave a carbon-hydrogen bond, we end up with a CH3 fragment, which we can link together at the carbons. So we can see a CH3 fragment there, a CH3 fragment there. Each carbon has 4 bonds, right? By including this carbon-carbon bond. So if we cleave a CH bond here and add another CH3 fragment, we'll end up with this. In fact, we can keep going on, keep inserting CH2 fragments in between our carbon-carbon bonds and keep extending out a chain. All right, another way of representing these structural formulas are condensed formulas. Methane's pretty simple, CH4. Now, this particular formula, right, we could have just written it as C2H6, but writing it in this fashion provides a little bit more information because we can identify a CH3 fragment here and a CH3 fragment here that we can identify in our structures, right? So when you look at a formula like this, even though it doesn't look like it, it implies that the carbons are bonded together, right? If you remember, each carbon has to form 4 bonds, so this one is forming 3 bonds with the hydrogens. The 4th bond must be through the carbon-carbon connection. Again, when we look at a comparison of this structural formula with a condensed formula, we can identify a methyl fragment here, sorry, a CH3 fragment here, CH2 fragment here, and a CH3 fragment here. Now, for the naming business, sorry, we'll go to line drawings next. In addition, there's a more compact way of representing the structural formula and condensed formulas, and that is by denoting the carbons as points that are connected by a line. So here we have a carbon bonded to a carbon, and it is implied that we have 3 hydrogens here, so that each carbon has 4 bonds, and that this carbon is also bonded to 3 hydrogens. It's just implied in this highly compact representation. If we look at this one, we have a carbon there, and a carbon there. Each of them are linked by single bonds. And it is implied that this carbon, since it's bonded to 1 carbon there, has to have 3 more bonds, and they're bonded to hydrogen. Same thing with this one, right? And the one in the middle, this carbon is bonded to 2 carbons, so it must have 2 hydrogens bonded to it, as we can see in the structural formula. All right, now getting to the names. The alkane, right, with the ane ending, that has 1 carbon is called methane. And the CH3 fragment in a structure is called methyl, YL. It's called a methyl fragment or a methyl group. A 2-carbon skeleton, right, is called ethane, and a fragment, say in this molecule, of CH3CH2 is called ethyl or YL, ethyl. 3 carbons is called propane, right? No doubt you've heard of that before. Certainly you've heard of methane as well. It's also known as swamp gas, right? It's or marsh gas. Propane is used in outdoor grills, right, as a source of fuel. And if we have 4 carbons in a chain, we call that butane, B-U-T-A-N-E. And if we go to 5 carbons in the chain, well, now we start to use Greek prefixes. Pentane, 6 carbons, hexane, 7 carbons, heptane, 8 carbons is octane, and I know you've heard that before, right? It's one of the principal components in gasoline. Gasoline is a mixture of alkanes with the principal component being octane. All right, now, if we look at these line drawing representations, we can look at what are called branched hydrocarbons and look at how we would name those. So if you have a branched hydrocarbon, you look at the longest part of the chain. So we have 1, 2, 3, 4, 5 carbons. So we would name that part pentane, right? So we've got pentane right here. But we have another CH3 fragment. Remember, we call that a methyl group. And we locate its position, right, at the 2 or 3 position, right? Here it's at the 2 position by writing the numbers. So this is called 2-methylpentane. If it were at the 3 position, it's a different compound, completely different compound. Even though it has the same formula, the atoms are arranged spatially different, right? That's called an isomer, and that would be named 3-methylpentane. Note, however, if you put it here at the 4 position, if you think about it carefully, you don't have a new compound. It's the same as 2-methylpentane. Imagine you put it here, and now just flip the page around or flip the structure by 180 degrees. Spatially, there's no distinction, right, from what you had to begin with. So the way we name these is with the lowest number, right? So 2-methylpentane would be the same as 4-methylpentane. We just don't use 4-methylpentane. And likewise, if we put the methyl group at the 1 position, Well, it's just 6 carbons long in our hydrocarbon. We would just call it hexane. It's not branched. All right, so in addition, a lot of organic compounds are characterized by a hydrocarbon skeleton and then one or more so-called functional groups. And we're only going to require you to know 3 of them for the purposes of this next exam. The first functional group is called an alcohol. It's an OH fragment. So if you take butane, CH3, CH2, CH2, CH3, remove the hydrogen from the carbon. So you've got a carbon-hydrogen bond. You remove that hydrogen, and instead you make a carbon-oxygen bond. You now have one member of a class of compounds called alcohols. So you name this from its number place on the hydrocarbon chain. So it's at the 1 position. So you name this 1-butanol. You drop the E in butane and add OL. So here's a case where we have 1, 2, 3, 4, 5 carbons in the main chain. So it's pentane. The OH group, the OH fragment, is at the 2 position. So we call this 2-pentanol. By the way, if you just had CH3OH, that would be called methanol. CH3CH2OH is ethanol or ethyl alcohol. CH3CH2CH2OH would be propyl alcohol, etc. All right, if you have the functional group NH2, these classes of compounds are called amines. When they're attached to an alkane like this, they tend to be gases at room temperature, and they smell really, really bad. As a matter of fact, if you've ever smelled rotting meat, right, that putrescence derives from bacteria that have metabolized the proteins, right, which have nitrogen in them, and they generate these what are called alkylamines. And this is just one example. 4 carbons long is butane, right? The carbon-hydrogen bond is broken. You form a carbon-nitrogen bond. So we would name this butan, drop the E, and add amine, A-M-I-N-E. 1-butanamine. The last functional group is called a carboxylic acid. So that's shown right here, COOH. They have the property that when these dissolve, if they're soluble in water, they have a tendency to ionize, that is to fragment, to generate hydrogen ions. So for that reason, they're called acids. So how are they named? Well, you look at the number of carbons, 1, 2, 3, 4, 5 in the structure. So you start off naming it pentane, right? You drop the E, add oic, and then acid. So this is pentanoic acid. All right, that wraps up our naming business. So now we'll just take a mock quiz, which is fairly reminiscent of the kinds of questions you'll get on your next exam for naming. So go ahead and pause the video and attempt to name the following 6 compounds. All right, so the first one, you look at it, you have to identify, is it an ionic compound, is it a molecular compound, or is it an acid? So you look at it, you go metal, non-metal, right? Barium is a type 1 metal ion. It's always +2. It's in the alkaline earth column or group 2 family of elements, so you just name it barium fluoride. All right, so for the second one, well, we've got a metal, vanadium, and you need to recognize that this is a polyatomic ion simply by memorizing it. It's hydroxide, and it has a -1 charge, and we're counting 2 of them in the formula unit. That requires the vanadium then, type 2 metal ion, to be +2 charged. So we would call this vanadium 2 hydroxide. All right, so number C, all of the elements are nonmetals, so we name it like a molecular compound, so you have to use Greek prefixes to identify the relative numbers of atoms in the formula. So we would call this one dinitrogen pentoxide. All right, so for formula D, you look at this, you recognize lead is a metal, and we've got a polyatomic ion here. Now, if you remember the one with the ATE ending, it's not this one. ClO3 minus is chlorate. This one has one oxygen atom less. So this one is called chlorite. So you would name this, well, first of all, you have to figure out the charge on the lead, right? It's a type 2 metal ion. You have two chlorites. Each one's a -1 charge, so that requires lead to be +2. So you would name it lead 2 chlorite. All right, compound E is an ionic compound. Lithium's a metal, chlorine's a nonmetal, so you name it lithium chloride, but it's a hydrate. So we recognize that there's just one water molecule for every lithium chloride in the formula unit, so you'd name it lithium chloride monohydrate. And then finally, the last one is an acid, right? It contains hydrogen, it's a binary acid. You just sort of have to memorize that this has the property of an acid. And it's an aqueous mixture, right? So you name it hydrofluoric acid. If this were a pure compound, right, not a mixture in water, you'd name it like an ionic compound, and you would call it hydrogen fluoride. All right, take a brief moment to pause the video and attempt to take these names and write chemical formulas for them. All right, so for the first one, well, if you've been paying attention, you'll recognize your formulas right there, right? You should be thinking chlorite. All right, well, I know chlorate. Chlorate's ClO3 minus. Chlorite's one oxygen atom less, so that's ClO2 minus. And I'm told that lead is a +2 charge here, so I need two chlorite polyatomic ions in my formula. So I would write it with one lead, a bracket around the chlorite polyatomic ion, and count two of them. All right, when we look at the name for aluminum fluoride, aluminum's a metal, fluorine, right, is a nonmetal, so we have an ionic compound. Aluminum is one of your type 1 metal ions. When it forms an ionic compound, it's always +3. So we don't have to use Roman numerals. We just call it aluminum fluoride, and we would write the formula, since aluminum is +3 and fluoride is -1, we need 3 fluorides for every aluminum, so it's AlF3. All right, now for problem C, you're looking at this and you're going, what in the world is tellurate? That's not one of my polyatomic ions. All right, if you look at the periodic table, look and see where tellurium is, you'll recognize that it's in the group 6 family of elements, right? In the oxygen family, those are called chalcogens. You've got oxygen, then sulfur, then selenium, and tellurium. Well, you know sulfate is SO4 2 minus, right? Well, selenate is going to be SeO4 2 minus, and tellurate then would be TeO4 2 minus. But wait a second, we've got hydrogen tellurate, so we've got a proton attached to the tellurate polyatomic ion. So that modifies the charge. It's HTeO4 minus 1, right? And we have sodium in our name, so we need one sodium ion to balance the charge for our hydrogen tellurate polyatomic ion. So we'd write the formula NaHTeO4. All right, and then last of all, carbon disulfide. Carbon's a nonmetal, sulfur's a nonmetal, so you name this as a molecular compound, right? So this is just CS2. Okay, folks, that does it for this lecture. Please let me know what you think of using the screen capture. I've never really done it before. I've had a whole bunch of problems doing it. This is the first time I've tried using QuickTime, so I'm hoping this works. I'll ask you for some comments about this on lecture on Tuesday.